Hello everyone. When you write an ARM instruction like this, it looks like the processor directly understands add R2 and R3. But that is not what actually happens. The CPU does not receive assembly instructions. It receives a 32-bit machine instruction made of bits. For example, consider this 32-bit value. Now the processor has to figure out what operation is this, which registers are involved, is the operand a number or another register. This job is performed by the instruction decoder. Today we will build a simplified ARM7 instruction decoder in assembly and understand what happens internally inside a CPU. What does an instruction decoder actually do? From the memory, instruction is loaded into the instruction decoder. It generates the information about the operation, register selection, and the operand type, and generates appropriate control signals to the ALU or execution unit, which then executes the actual instruction. Before building our simplified decoder, let's see how ARM7 actually organizes instructions. For example, ARM7 data processing instructions use a format like this. Now let us see what are the important fields here. Opcode tells the CPU what operation to perform. For example, it could be add, subtract, move, and etc. Then we have Rn. This is the first source register. Next we have Rd, which is the destination register. Here I bit is very important. It tells the decoder what operand to represent. If it is 1, then operand 2 is an immediate value, else operand 2 contains a register. Real ARM instruction encoding has many details. That is too much for a beginner decoder. So we will create a simplified ARM7 inspired format. The concept remains same. This is our simplified instruction format. As you can notice here, our instruction is still 32 bits. Here, we are considering our opcode to have three options, that is add, subtract and move. RD represents the destination register, RN the source register. I can have two values 0 or 1, and the operand here is nothing but the immediate value or register number. Let's just run the actual code and understand the working of the decoder. First of all, let's see if there are any errors. No errors, so we'll go ahead with debugging. Area here represents an assembler directive which defines a section of memory to store this information. Decoder is the name I have given to that section of memory. Code indicates these are nothing but actual ARM instructions. Read only because we don't want any modification to be happening to this particular code during runtime. Entry indicates where exactly execution starts. Execution starts at the very first label that appears after this assembler directive. Start, regi, immediate, store, stop, result are nothing but labels. End indicates the end of source file. Again, you can see some more assembler directives here. Area we have already discussed. Data is again a name. Data here represents this section stores data values rather than code. Read write because we should be able to store our final result in the memory location represented by this label. Space is again an assembler directive which reserves uninitialized memory location to store the final data, and 24 here represents 24 bytes. That is nothing but the size of our uninitialized memory location. Now let us move to our actual code. So here we are loading our 32-bit instruction into register R0. In the next step, we are trying to extract our opcode by performing logical shift right on R0 by 28-bit position. So the opcode we have extracted is 1. Next, we are trying to extract our destination register number. For that, we need to perform logical shift right by 24-bit positions. Followed by that, we are performing AND operation because our focus is to extract bit number 27 to 24. Okay, which represents our actual destination register number. Next, we are performing shift right by 20-bit position followed by AND operation to extract our source register number. Followed by that, we are performing shift right by 16-bit position and ANDing R4 by 1 to extract our I bit, which stores information about whether our operand is an immediate value or source register number. So now, since we have already extracted our opcode, we are checking if it is addition, subtraction or move. If it is addition, R6 value is updated as 1. Now let's run the code. Compare performs subtraction internally and updates CPSR. If Z flag is set as 1, only in that particular case EQ condition will be true and that particular instruction will be executed. In our case, add is the actual instruction to be performed, so R6 is stored with the appropriate control signal. In the next case, Z is set as 0 because R1 is not 2 or 3. Hence, these move instructions are ignored. Now we are comparing if our extracted I bit is 1 or 0. If it is 1, it represents immediate data. If it represents 0, it means registers are used in this instruction. So here compare performs internal subtraction and updates CPSR. As you can see, Z is set as 1 because of which there is a branch to immediate. If that is not the case, on our instruction we perform AND operation with the value F to extract the first 4 bits which represents our actual register number, and we branch to store. But right now that is not the case, so we are under the label immediate. Okay, so here we are performing AND operation between R0 and this value FFFF, which extracts our last 16-bit number and places it into our register R8. This 16-bit number we have extracted is our 16-bit immediate value. Next, we jump to the actual store operation, wherein we are trying to store all extracted value into the memory. And let's check at which address we are storing our result. So result label is associated with the address 4 and all zeros. So we will go to memory window and open that address. Okay, so this is our address. So now when I run the code, arg6 content, that is our ALU control signal associated with the opcode, is 1. If you check here, R6 is 1 and that is stored in the memory. Next to that, in the next location, we are placing our register content R2, and we already know R2 holds our destination register number, and next to that we are storing R3, which is our source register number. Followed by that, we are storing the value 1, which indicates that we are using immediate value. And finally, we are storing our immediate offset or our immediate value which needs to be added. And we jump to an infinite loop. And if you check here, our simple decoder has already extracted the opcode, destination register number, source register number, whether the second operand is register or immediate value, and our actual immediate value is also extracted. That's all about this code.